The chapter we're looking at now is chapter 7, hyperbolic functions. Right, so this chapter is a self-study. You'll not be given any formal lectures on this examinable chapter. So what should be noted is that it's very much examinable, even though it's self-study. So the reference for this section is in the textbook. We'll also proceed to that after establishing what our learning outcomes are. And also, just as a quick reminder that I said that you should go back to chapter 6, the section we're looking at curve sketching and completing the checklist for the learning outcomes to check that you do understand everything that we did and everything you know. Okay, so the learning outcomes for the section here, you should know the definitions of the hyperbolic functions. So we call that sinh, cosh, and tan. Sech, coth, and cosech. And you should also know the sketches of the graphs of these hyperbolic functions. So when you look at all these hyperbolic functions that are presented here, you'll notice that there's an H that goes with them. So that's to let you know that you're looking at a hyperbolic function. You should also note the hyperbolic identities and their derivatives given in the textbook. We'll look at that. Note the derivatives and the proofs of the hyperbolic functions. Right, so derivatives and proofs. And note the inverse hyperbolic functions. Sich, inverse, cosh, tan, inverse, and their sketches. Right, now to express the inverse hyperbolic functions in terms of natural logarithms. So know that the sinh inverse is equal to the natural log of x plus square root of x squared plus 1, and so on. And to also note the derivatives and proofs of the inverse hyperbolic functions given in the textbook, and know how to use the inverse hyperbolic functions given in integration techniques, and know how to solve the examinable worked out problems on this section. So the worked out problems are the ones that are presented here in this tutorial. And then here, you ask to prove these here. Right, so always remember that you need to come back here after we are done with the chapter and complete your checklist. You know the definitions, the proofs, the derivatives. Right, so now let's break it down in detail. So once again, we're looking at hyperbolic functions. So the hyperbolic functions, these are formed by taking combinations of the two exponential functions, e to the exponent x and e to the minus x. Okay. And the hyperbolic functions simplify many mathematical expressions and occur frequently in mathematical and engineering applications. So the definition of the sinh function is e to the x minus e to the minus x divided by 2. And for cosh x, this is equal to e to the x plus e to the minus x divided by 2. So a good trick to try to remember these signs here, because you can see that they are quite similar to each other. So it's e to the x e to the minus x, and then divided by 2. So you may wonder how you can remember which is which. Right, so for sine here, for sinh, I mean, you can think of it as sine or sinh, right? Sinh is negative. So when you look at this one here, right? So this sinh, you only look at this part, and then for n here, you're looking at negative. Does that make sense? So sinh is negative, describing the sign that occurs here. So it's sinh x, and then for cosh, you can remember this by, you can say your cosh or your cosh is positive. So here, instead of using the first letter, you're using the letter S, which you're finding here. So cosh, okay, cosh is positive while sinh is negative. Does that make sense? Okay, so that's how you can remember the signs here for the hyperbolic functions. This is how we define them. And you know that once you have a sinh and a cosh, well, a sine and a cos, you can also define your tan. So you can also define the hyperbolic equivalent of tan. So to differentiate between tan and tan, the way that I'll say it is that when it comes to this one here, I'll drag it out when pronouncing it, so it will be 10 instead of just 10. Okay, and then from there, we can so sinh, this one here, you pronounce it as sinh, like that. And then for cosh, like I've been saying, pronounce that as cosh. Right, and the identities from trig functions, you can see here that there's a bit of similarity. So when you take the 2 sinh x, you multiply that by cosh x, this is what you will get. So we've defined the sinh like this in this manner. We said that that's e to the x minus e to the minus x divided by 2, and then the cosh x, this is equal to e to the x plus e to the minus x divided by 2. That means that when you multiply these two, sinh x cosh, you're going to use these definitions that we have for them. So that's like that, divided by 2, multiplied by e to the x plus e to the minus x divided by 2 in that manner. And from there, the middle terms will cancel out. Right, so you're going to have, so you use laws of exponents here. So it's e to the x. Let me just expand it so that you can see it. So we're taking this one, multiplying it here, and then this one to that one there. So plus e to the x, e to the minus x, and then this one here to this one here. That's e to the minus x, e to the x. And then finally this one to this one here, which is minus e to the minus x, e to the minus x. And all of this is divided by 2. So this is e to the 2x. And then here, this is e to the x multiplied by e to the minus x. This here is minus this expression here is the same thing. What you can just do is to rearrange it so that you can see that this is the same. So you can say plus minus. So here I'm not changing anything. I'm simply just changing the order so that we have e to the x, e to the minus x, and e to the x, and e to the minus x. Does that make sense? Okay. And then from there, these two terms are going to cancel out. When you apply your laws of exponents here, you're simply going to have e to the x to the exponent x plus x, which is e to the 2x. And that's what we have here. And then for the last one, that is going to be minus e to the minus 2x divided by 2, which is what we presented here. So this is 4 here, not 2. That is 4. So what you will notice that we can say you have e to the x minus e to the minus x divided by 2. So you can say 2 squared here. And for this one there, we can square it. Just a minute. See if it works out. Okay. Don't factor it out like that. What you can rather do is to say this is 2 times that, and then 2 times that. And we're reducing this to now sinh. So since we have the 2 there, we can factor out this 2 here so that we're able to cancel it out. So sinh 2x like that, and divided by 2 in this manner. So now, if you now want to simply have sinh 2x, that means that you will then have to multiply this entire thing by 2. You will say multiply that by 2 so that finally, when you now arrive at the stage here, you can say 2, and these 2 will cancel out so that you have sinh 2x like that. This was a great example to show how all of this works. Does this make sense to you?
Yes, it does.
Okay. If you happen to have any questions, you can let me know. Okay, hang on 1 second. I'm going to erase this now, but before I do, I just want to quickly take a snapshot so that if you want these notes on this part, you can have it. Okay. So these are the curves that you are supposed to know for our hyperbolic functions. So for sinh y is equal to sinh x, this is how it looks like. It goes through the origin in that manner. And you've got y is equal to e to the x divided by 2. Right. So our definition of sinh, where that you have e to the x divided minus e to the minus x divided by 2. So you can split this out into e to the x divided by 2 minus e to the minus x divided by 2. And that's exactly what you're seeing here for these asymptotes. and the curve goes between the asymptotes here. And then for cosh, this is how it looks like. So its value is determined by this algebraic expression that we have in the numerator. Then for tan, what you then have is that thing. So it's kind of like taking your tangent function and then you rotate it by 90 degrees clockwise. That gets you something like what you have there. And for tan, that is going to be sinh x divided by cos x. So you still use the same identity from before, but for hyperbolic functions. Right, so it's going to be sinh x divided by cos x, and when you simplify that out, that gets you this here. So I want you to try this out here as homework. Use the original definitions that we had for the hyperbolic, for the sinh and cos functions to show that tan x is equal to this here. And for cot, that is going to be cos x divided by sinh. So it's same identity as well for cot. So cos divided by sinh. And for the cot function here, you can see that it's in the first and third quadrants. And the asymptotes for tan here is y is equal to 1 and y is equal to -1. And then for sec here, we're looking at the inverse of cosh. And that means that you're simply going to invert this here for the inverse. And what you have is that your curve looks like this, and y is equal to 1 forms your asymptote. In the hyperbolic cosecant here, this is the inverse of sinh. So we're going to flip this around. So the denominator is going to be the numerator and vice versa. So here what you need to do is really practice how to plot these, know it off by head. So the homework that I'm gonna give you here is that use decimals.com to plot cos x, sin x, tan x, cosecant x, cot x, sec x, and compare them to their hyperbolic equivalence. So see here if you can draw any similarities. In this context, draw doesn't mean to actually draw. It means to see if you can find. See if you can find any similarities in the way that the curves are plotted. Does that make sense to you?
Yes, it does.
Okay. Perfect. So we also have the table which contains the identities for hyperbolic functions. So we've got cos squared x minus sin squared x, and that's equal to 1. And sine 2x is equal to 2 sine x cos x. Cos 2x, this is equal to cos squared x plus sin squared x, and cos squared x, which is equal to this here, and sin squared x is equal to that. And tan squared x, which is equal to 1 minus 6 squared x, and the cot squared x is equal to 1 plus cosecant squared x. Right. So essentially, what's happening here, right, is like for most of these examples here, depending on what you need to, what identity you need, right? If you know that your cos squared x minus sin so sin squared x is equal to 1, you can go to any of these identities that you have, the most, if not all. So what you essentially need to do here is, let's say you need an identity for 10, right? So what you will then do here is that you will say, since you know that you can bring out the 10 here from dividing by cos squared x, that's what you're going to do throughout this equation. So it's going to be 1 minus the 10 squared x, and this is equal to the hyperbolic function of the cosecant, right? So you can see how this here comes out from just starting with this identity here. Does that make sense?
Yes, it does.
Okay. And you can also divide by the sinh to get you the, so if you've got cos, that will give you cot. If you divide by sinh, that's what you get. And with this one, we showed how you can get there. And then we've also showed it for this one here. So this table here, that's also going to be your homework, proving all these identities here, the ones that remain. So if you know you have this here, see if you can go back to that one day, or if you prefer to start here, see if you can go to that one day. So it's very important that you attempt these. So the other identities here, it said that they are obtained in a similar manner. So by subbing in the definitions of the hyperbolic functions and using algebra. So for any real number u, we note the point with coordinates cos u, sine u lies on the unit circle, x squared plus y squared is equal to 1. So the trig functions are sometimes called circular functions because of this identity here. Right, with u substituted for x in the table. So the point having coordinates cos u, sine u lies on the right hand of the parabola x squared minus y squared being equal to 1. So this is what the hyperbolic functions get their names, because they lie on the hyperbola. So hyperbolic functions are useful in finding integrals, which we'll see in chapter 8. They play an important role in science and engineering. So the hyperbolic cosine describes the shape of a hanging cable or wire that is strung between 2 points at the same height and hanging freely. So you can also see this in exercise 83. So if we go back here, so for Koch, you can see that if you've got two electrical poles here for a wire or cable that's in this manner here, you can use Koch X to describe it. So the shape of the St. Louis arc is an inverted hyperbolic cosine, and the hyperbolic tangent occurs in the formula for the velocity of an ocean wave moving over water at having a constant depth. So this is it here. The depth needs to be constant. And the inverse hyperbolic tangent describes how relative velocities sum according to Einstein's law in the special theory of relativity. But this is law of physics, theoretical physics. But the applications, that's not something that you have to worry about. This just gives you something to think about. Right, so when it comes to the derivatives and integrals of hyperbolic functions, what you are working with here will be the definitions, the components, E, when you're differentiating these hyperbolic functions. So for sinh, we had defined that to be e to the x minus e to the minus x divided by 2. So d dx here of sinh x, that will be, you can factor out the 1 over 2. At this point, you are an expert at differentiating. So d dx of e to the x minus e to the minus x, like that. And this is 1 over 2 e to the x plus e to the minus x. And you can see that this simply turns into cosh x. Does that make sense? Okay, excellent. And then d dx of cosh x here, that's going to be d dx of e to the x plus e to the minus x divided by 2. That's 1 over 2 d dx of e to the x plus e to the minus x. And this is 1 over 2 e to the x minus e to the minus x. And this here goes back to sinh x. So what you appreciate here is the fact that there are no negative signs for the derivatives of cos, no or sine, or sinh, I mean. What you will have established previously was that d dx of cos x gives you minus sine x, but here the signs are all positive. Right, so d dx of sinh u, that gives you plus cos u du dx, and plus here, no minus between these two. So keep that in mind. It's not like our trig functions for cos and sine in that manner. So what they applied here was chain rule. So you start with the outer function, which we established that was going to be cos u. You multiply that by the derivative of the inner function. Does this look familiar? the Cauchy du dx when you're using the chain rule. Okay. That is excellent. So I'm gonna, when it comes to d dx of 10u, that's set to be equal to that. So I'm also gonna lift the proof of that to you. So how you're gonna go about this one here is that you can say this is sinh x divided by cos x. You can apply your chain rule or the quotient rule. That's up to you. So there are two ways in which you can go about this one here. So you can use chain rule or quotient. So I'm gonna give you a quick reminder of what this is and how it works. So essentially for chain rule, yeah, what you're gonna do is that you're gonna say you have d dx of sinh x multiplied by cos x inverse, right? And this is d dx. So you're gonna apply your chain rule, like I said. It's sinh. Okay, so it's gonna be a combination of chain rule plus product rule. So you're gonna say d dx of sinh x first multiplied by this one here plus sinh x d dx of cos x minus 1. And you already know how to do this one with this one because you can just invert it and then we're looking at the d dx of 2 divided by e to the x plus e to the minus x, like that, for that one day. But as you can see, that it involves a lot more work. And then for the quotient rule, d dx of sinh x divided by cos x, this is going to be cos x multiplied by sinh x prime minus sinh x cos x prime divided by cos x all squared. Does this look familiar?
Sorry, which part?
The quotient rule.
Oh,
The way
yes,
that
it
I've
does.
written it. Okay. Is there anything that you have any question on here?
No, there's no question.
Okay. So remember to do your homework there. So let us just dive into the proofs. And then for this integration section, we'll cycle back to after we've done integration in chapter 8. But if you are going to write a tutorial about this, be sure to let me know so that we can possibly look at it. So I want us to tackle integration first before we have to look at these. Okay. So we are now looking at inverse hyperbolic functions. The inverses of the 6 hyperbolic functions are very useful in integration. So since d dx of sinh x is equal to cos x, which is always greater than 0. So you can see that when you look at the plot here, that your cos is never below 0, meaning that it's never negative. It's always positive. So when we see that the y spot cos x is greater than 0, that's what we mean. The fact that it's never equal to, it's never less than 0. So the hyperbolic sign is an increasing function of x. So this is how we denote its inverse. For every value of x in the interval minus infinity and positive infinity, the value of y is equal to sinh inverse x. It's the number whose hyperbolic sign is x. Right, and we have the graphs here presented. So essentially, what this statement is saying here is that, well, this one, when you have y is equal to the inverse of sinh x, the value of y, this is going to be a number whose hyperbolic sign is x. So basically, this here we presented that to be y is x is equal to sinh y. That's what we're saying. So for the inverse here, what we're looking at is this one here in yellow for sinh x, and then for the inverse, which is going to be about the line y is equal to x, that is going to be this one here. This is the hyperbolic function of the inverse. So when you reflect it about the line y is equal to x, that's what you will get. So you can just put a string somewhere. I'll try to do a demonstration of this to show you how it actually works. So you can just put the string on a piece of paper and then flip it about the line y is equal to x, as if it's coming towards you, and then you will get something like this here. And then for cos, this is it here, and then when you reflect it, this one seems to be more intuitive. You can just see how you will get this one if you reflected this one about the line y is equal to x. And what we can say about cos is that it's not a one-to-one function. um, the graph here obviously does not pass the horizontal test. So if we go back to better understand, so if we go back to our Porsche above, we saw that that's how it looks like. So if you apply the horizontal line test, you can see that we have more than one point of contact here. But we've put a restriction here so that we're only looking at cosh x with x greater than or equal to 0. Right, so that means that now it becomes 1-to-1 and has an inverse. Are you following? Okay, excellent. And that's what that will give you. So you also need to know how the inverses are plotted. And for the hyperbolic secant function, this is it in yellow, and its reflection there will then give you this y is equal to the inverse of the hyperbolic secant function, which looks like that. And for tan, you can from that you can also produce your inverse, and that's what you will have. And then for cot inverse, that's that, and hyperbolic cosecant, that's that. So here it's just the plots that you need to know. And for this part here, what you need to understand is that the sec multiplied, or the sec of cosh inverse of 1 over x, you can also do this here and get back to x. So if you're using this here as your input, you can also write it in this manner. So since it's cosh of cosh inverse, that means that these two cancel out and you left with 1 over x, which goes back to x. So try this out as well. So try it out. That's also homework. And we've got identities for inverse hyperbolic functions. So, but these here. Right, so that's also highlighted in the table. And now let's consider derivatives of inverse hyperbolic functions. Right, so an important use of inverse hyperbolic functions lies in antiderivatives that reverse the derivative formulas that we presented above. Right, so Here we can essentially present them in the table. It's so the derivative of this sinh here, right? The inverse, you know how to do that, right? So you had um, your sinh initially, where I presented that to be this here divided by 2. Right, and so for the inverse, what we had was this here. And let's just quickly check the checklist to see if you're about to also know the proofs here. Okay. The learning outcomes, do you see that this is something that you are also required to know? Um, okay, so let's just take a quick example. Okay, so here we have the derivative of cosh inverse u, and this is equal to 1 over square root of u squared minus 1 multiplied by d dx. Right, so we have here that f inverse prime is equal to 1 over f prime multiplied by 1 divided by f prime of f inverse of x. And your inverse here is cosh. We're looking at the inverse of cosh, and the derivative of the function itself without the inverse, meaning that the derivative of cosh, this is sinh. And when you take these two here, when you consider these two, so the 1 over sinh of cosh inverse x, this is equal to 1 divided by square root of cosh squared of cosh inverse x minus 1. So you can simply just give sinh u some random variable. So when you go back to the identities that we established before, these ones here, you can see that for sinh, what you can see is that sinh squared u is equal to cosh squared u minus 1. So when you take the square root of that, you're going to have u is equal to square root of cosh squared u minus 1. And that's what we introduced here. The only difference now is that we have an inverse, which you still need to place the as your argument, as your u. So your u here is essentially equal to cosh inverse x. And then from the cosh squared of cosh inverse x, right? That gives you in x, but if you now squaring that, so this here, this cosh of cosh inverse of x, this is all squared, and this 2 here belongs to this cosh. So if you know that the product of these 2 here, not yeah, the result, right, that's equal to x because it's a function, and as its argument it has its inverse, and you know that it's just going to give you that independent variable, and that's x. Does that make sense? Okay, excellent. And then finally, that's what we have there. And then for when it comes to the integrals, you do not have to be concerned about these for now. We'll come back to later on. So like I said, since we are now through this section, when you've done the exercises and perhaps you've rewatched the video, you need to come back to the learning outcomes here to just check off everything that you need to know. This one, perhaps you can just leave until we get to chapter 7, and then we'll circle back here. So also make sure to do these type questions. So any that you do not understand, you can message me about them to ask. And if I deem it necessary, we may include them as part of the lesson.